Mm-hmm. That's good. Okay, it's looking good. Yeah. Okay, students, welcome to the. Let me put this. Yeah, welcome to the 6th lecture on multibody dynamics. I have opened the chat, but I will close it the moment that anybody is making misuse. So if Klaas Koerten says peace, that's very nice, but don't do that. Just don't do it. The chat is only there for raising questions, and raising questions in the chat is by keeping it short and don't blab among each other. Otherwise, I'll just have to close the chat. It's very difficult for me to, on the one hand, give a lecture, and then on the other hand, also watch the chat. So don't misuse that. Okay, so those are rules for the chat. Today's topic is numerical integration of ordinary differential equations, and that's chapter 15 out of the book. And then the first thing, of course, we start with is Kahoot, right? So the Kahoot quiz. So let's see. Kahoot, we go through here. I have to resize it to make sure that everybody sees the number. Yeah, something like this, right? Yeah, okay. Where is Kahoot? Here is Kahoot. My Kahoot. Yeah, quiz number 6. That's okay. We do classic. Put the tolerable sound off. Resize a little bit more. Yeah. So please log in. expecting around 130 players. Yeah, it seems like it sort of became a stable number. Okay, let's start the quiz. First question is about the TMT method. The origin of the TMT methods can be found in I notice a delay of about 4 seconds. Yeah, very good. So let me reflect on the origin of the TMT. There's no real image to show. Well, yeah, this, but that's not so interesting. So half of you said Lagrange analytical mechanics, which is correct. And the other half says Newtonian mechanics and D'Alembert forces. Well, the D'Alembert forces may be right, because that's what Lagrange uses, but Newtonian mechanics is not enough. It's a little bit more, because you need the whole concept of power and energy, and that came after Newton, right? So Lagrange was the right one. Second question. This is about virtual power. So you need your virtual power toolkit to calculate this. Clearly that's 1 degree of freedom, the angle A, and the big question on the right hand side you see forces, and the force Fx on the system will appear in some form on the right hand side of the equation of motion in terms of these independent degrees of freedom. And how will it appear? And just use your virtual power toolkit, and you can calculate what the contribution will be of this force to the equation of motion expressed in the generalized degree of freedom A. Yeah, everybody's in a live stream, so for the live stream the delay, as I notice, is about 4 seconds. So you have to answer now, like in now. Yeah, so that is a sort of a difficult question. I expected that, so it's less than half who have the correct answer. A big part take an answer from last year, which is incorrect, of course. So let me explain a little bit. This force Fx, we have 1 degree of freedom, this angle A. Now you can imagine there's a speed, a dot, and then this point has a speed, L times a dot in this direction. And then the power of this force is just the dot product of this force times this speed, which is in this direction. And apparently then the component is, the speed is L times L for a dot, and then the component is times the angle, the sine A, and then it's negative because it's opposed to Fx, so therefore the correct answer is minus Fx L times sine A. Okay, next question. This is again about having not a unique solution. The example with the pendulum with the mass. And the big question, why is there no unique solution? Yeah, very good. Most of you have the correct answer. It might be a bit confusing because there are two correct answers. The first is that the mass matrix has 0 eigenvalues, and the second one is that the determinant of the mass matrix is 0. And actually these two statements are equivalent, right? Because the determinant is eventually determined by the product of these eigenvalues, which is then 0. Okay, next one. This is about your homework problem from last week, but now I want to know the velocity by which the swing leg will impact the ground. And so the walker is walking down the slope, and then the swing leg will hit the ground, and the question is, what will be the magnitude of this impact velocity? Maybe a hint, just before impact, draw the configuration and just determine what the velocity of the point which is about to hit the ground. And then you look at the component normal to the surface. Yeah, okay, most of you are correct. It's you determine first the speed of this point, which is alpha dot times L, and it's in this direction, and then you add up the speed of this point relative to this point, and then finally you find those two, and then you need to normal to the ground. Okay, I think we can move to the last question. And that's about today's topic, numerical integration. And the question is, a numerical integration step according to Euler is given as in the formula. And this finds its origin. Where does it find its origin? That's the big question. Yeah, I said previously that the delay is about 4 seconds, but that's of course for my configuration. For others it could be a little bit more. Yeah, that's a very clear answer. It's the Taylor expansion of a function gives you like a first order approximation. So very good. I think this was the quiz, right? Yeah. Somebody is on the podium. Let's see. Do we have a winner? Yeah, we have a winner. JJS is the winner. Very good. Then we move on. It would be nice if you could get some feedback. But first let's save the results. Yeah. And to be sure, to be dead sure, I'm going to save it to my drive. Good. Oh, yeah, that's okay. Okay, yeah, we can leave that now. I have everything. Okay, then we go to everything is in something like that is okay. Okay, the topic of today, numerical integration of ordinary differential equations. If everybody remembers, then the first quarter we actually spent most of our time on deriving the equations of motion, right? And either it was in a DAE form, that's how we started, with mass matrix, that should be capital, right? Jacobian, zeros, and then here accelerations, Lagrange multipliers, and on the right hand side forces, and then here's some other second order terms. Or the other form we had was like this TMT method or Lagrange method, where we go to generalized coordinates, independent ones, and then we usually don't have any constraints, and then we have different. But either in the end we calculate accelerations, right? We calculate accelerations. Accelerations, yeah. Now, either x double dot or q double dot, and from that we can also do. However, that's not what we're really interested in. We want to know the motion as a function of time. So we want to know x of t. Or if you work in your generalized coordinate, q of t. Not so much different. So that is actually the quest. And of course these accelerations are nice, but they don't give us a function, the thing as a function of time. So the problem is, given a certain amount, a certain time, t is t0, and at that time I have my initial values, q0, and of course also I have my initial velocities, and of course the differential equation, m times q double dot equals these generalized forces on the right hand side. I can calculate the accelerations at q0. Then the question is, what is q of t? Can we find a solution to that? Well, in general, you could say I have here like a differential equation, right? And it's even linear in the accelerations here. Although these generalized forces and this mass matrix can be a function again of the coordinates and of the speeds, and indeed they are, of course. So it's a differential equation, and how do we solve differential equations? Well, if you go back to your math problem in the past, if you say like, well, if I have something, q of dot is like say t, then how do I find q? X of dot is t. How do I find x? Well, actually that you have to look up. That's a sort of a lookup table, a lookup thing. And of course you know some general rules for finding primitives, but in principle you have to look it up. Well, why do I say look up? Well, the counterpart, differentiation, is just a formula. So if you say, oh, x of t, how do I find that? Well, that's the limit of taking a small amount of time, delta t to 0, of, well, x t plus h minus x t, and then divided by this, well, let's call it h, that's okay, by h. That's a formula, and you can put in any function, and then you can determine what the limit case is. But so one way, this goes one way, that's no problem. But the other way, going backwards, That's not there's nothing for that. There are some general formulas, but most of it's lookup table. So differentiation is easy, integration is very hard, and usually it's lookup table, or even if I give you like this differential equation, t times cosine t plus tangent t times e to the power t. I mean, do you have any idea what the primitive of this function is? You have no idea, actually. It's very hard, and you have to look up some standard solutions, and you say, oh, that I know separate solutions, and then I add them up. But in general, that's a very hard thing. So where differentiation is easy, finding primitive is very hard. And in our case, even this is very nonlinear, because in general the mass matrix will be a function of the coordinates, and there will be speeds quadratic in here. So we have to come to the conclusion that analytic solution of these ordinary differential equations is not possible. And you could try. I mean, you could write out in MATLAB everything in the symbolic toolbox and then say solve, and you will see the program will crunch for hours, and your computer will overheat, and you will not find any solution to that. So we have to go to another way, and the other way is numerical integration. So we're going to use a numerical tool, the same way as we solve nonlinear equations, then we also linearize, and that's a numerical tool, and then locally we solve them. And the same we're going to do with integration. We're going to use numerical integration. Now, one way to do it is like this. So you have some initial value, plus you know the speed at that time, and then you say, oh, my next time step, q1, I'm going to find by multiplying with my time step h times q dot. And that is a sort of a naive way to numerically integrate. And why do I say a naive way? Well, it's something like this. If your q dot is your speed, you go like, say, 20 kilometers per hour, and then you want to know in the next half hour, where am I going to be? And you start from home, which is 0. Then where will you be? Well, you just calculate this stuff, and that's, oh, I will be at 10 kilometers. Because the hour cancels this hour, of course, and the outcome is kilometers. So yeah, that is the actually the whole ground for this numerical integration scheme is the naive way by which you interpret speed and distance and time. Okay. And the same, of course, this is now with the coordinates, but the same we can do with the speeds. The new speed is the old speed plus the step size times the acceleration. And that would be a nice way. Then we have found at t1 our q1 and our q dot 1. Then again we solve for the equation of motion, or in other words, we determine this is everything as speed, of course, of the state. We solve for q double dot 1, and then given that one we can go back to the top here, and we put in all the new numbers, and that is just a nice iterative way, and we run around like this. And then we found in a discrete way subsequent solutions. Now there is a graphic way to interpret what we are doing, and that is you draw a graph, and on the horizontal axis you say t, and on the vertical you say q, and then you say, well, at t0 the only thing I know, I have no clue what the function will be here, right? But the only thing I can calculate is q dot. So this slope, this is q dot at 0. And given that slope, and then given some finite step size, you can estimate, if this is h, this distance, and this is t1, then you can estimate approximately what is my new position. Then that's just a linear guess, as you see here. And then from the linear guess, again you calculate what is my derivative, and maybe the derivative here, your q dot, this is your q dot in 1, it's a little bit lower, and then your next step is here. And then you calculate again your q dot, and maybe going like that, q dot in 2, and then your next step is here. So you you generate then these discrete steps, and you generate the function. So that's the way how we go about with numerical integration. Where does this find its origin? Well, we already saw that in the quiz. Of course, you could say, origin. Of course, you could say, well, speed has a definition, right? So let's take this again, limit of delta t to 0 of qt plus delta t minus q at t divided by delta t. And this goes away. And you could say, well, I can turn this formula around. I can say, oh, the q at t plus delta t equals the q at t plus delta t times q dot at t. But note that we sort of, when we come to this, we sort of got rid of this whole thing of limit, that the time should be very small, these time steps. We sort of cancelled that out, and then we get this formula. So this only holds for delta t's, which were very small. Otherwise it will not work. Now, of course, the origin is not really from the definition. The origin is actually from the Taylor expansions, because the Taylor expansion of a function, and you could see that this function of time is like a function, goes like this. So if we talk function, we say x plus h equals the function value at x plus h times the first derivative of the function at x plus h squared divided by 2 times the double derivative at x plus, and then it goes on, and the h to the power n divided by n factorial times the nth derivative of x. And of course, in this Taylor expansion is the origin of such a numerical integration step. Now, with that in mind, and also with the high school thing in mind, because remember from high school we learned the following things. We learned that if you have a constant acceleration thing, constant acceleration, and is that constant acceleration motion, and is that reasonable? Well, if you have a constant force, then you have like a constant acceleration, like something falling in a gravity field, or a guy who's pushing with the same force to an object, or a car which is accelerated with a constant force. Then we know that the speed as a function of time will be the speed by which we start plus this acceleration, which is constant, times t. And the distance we travel is then of course the initial distance plus the velocity times t plus 1/2 of the acceleration t squared. And now looking at this formula, there's of course a big resemblance with this Taylor expansion, right? And in hindsight, when we look at our scheme, you could maybe say, oh, then we could add also the acceleration in determining the position. Well, we come back to that in a second. Okay, now I'm going to make the connection with textbooks. So an ordinary differential equation in the textbooks is usually written as such, is written like this. They write y prime is some function of x and y. And then they say with some initial value, the y at x0 is y0. So that's usually the statement. Now we don't work with x as the y as the independent variable and x as on the horizontal axis or the time. So we don't have these differentials. We work with time. So what we have actually is a y dot is some function of time and y, and that's everything we're doing dynamics. And again, well, actually not. Actually, we have a little bit. Actually, we have a little bit more complex one because we don't have a differential equation for the speed, but we have a differential equation for the acceleration. So what we have is something like m times q double dot is forces which are a function of time, the position, and the speed, something like that. And then with some initial values, and of course we have two sets of initial values, one on the coordinates, q0, and one on the speeds at t0. Okay, I see still no questions in the chat, so that looks good. Or either my computer, this thing is down. No, it works. Okay. Yeah. So if this is the textbook a way to present it, and all the methods are presented in this form, we have to recast our differential equation here to this form. So how are we going to do that? So we have to come from this second order differential equations to first order. How do we do that? Well, we just substitute variables. So we say, let's assume we want to get rid of q double dot. So we say q dot is p, meaning then that q double dot is then p dot. And now I can write everything in terms of either p or q, or either q dot or p dot. So the first, and then we form them in a vector. So we form a vector, and the order I never remember. We do q and p. You can also turn the order around. And then y dot, which is this vector of q dot and p dot, is just these differential equations. And what are they for q dot? Well, the first differential equation for q dot is very simple, because that's this guy. Q dot equals p. Because everything on the right hand side I now have to write in terms of p and q. And there should be no dots. And then what is p dot? Well, that's q double dot, and that's this whole shebang, or in other words, that's m minus 1 times the forces which are a function of time, q, and then q dot. And actually, it's not nice to write q dot here, because everything had to be in p and q, so I have to write here p. So it's a function of t, q, and p, right? So on the right hand side now I have the state and the time, and on the left hand side I have the differential. So what I did from n second order differential equations, I now moved on to 2n first order differential equations. Of course the equations do not change, but now I have casted it in our standard scheme. For some magical reason, we always call the step size h. So if you see in the rest of the derivatives, in the rest of the lecture, if you see h, then you have to think, oh, that's a delta t. Why that is, I don't know. Why do we call mass m? Well, that's how it is. Step size h. That's how it is. Okay, so our numerical integration step, where we started with as an example. In our nomenclature now, in our symbols will look as such. We usually drop the t plus 1, etc., and we write yn plus 1 equals yn plus h times f tn yn. That is usually the way how we write that. So the index n and n plus 1 means that's the index of the discrete solutions in time. And y can be a vector, but I omit all the underscoring for the vector, because I then have to underscore everything, and I don't want to do that. But either this can be a scalar or a vector equation. Tn is of course a scalar, time n, and then yn is a, so yn is the state at point n. There's a big confusion with this n, so for this n had to do with the number of equations. This is with the discrete steps we make. Okay, how do we call this? This numerical integration step has a name, and it will not surprise you that the name is, this is known as a, yeah, you can say it in the chat, although there's a delay, that doesn't work, right? As a Euler step. Of course, Euler was everywhere. I mean, and why? Well, because eventually he also has to find solutions for his equations. And then there was no method for that, so he had to invent that himself. The Euler step. So Euler was actually the first who did this numerical calculation stuff. After that, it has been somewhat quiet, and the next step in numerical integration really evolved when we got more computing power in the sense of mechanical calculating machines. That was around the 18-somethings, and I will, in the second half of the lecture, I will come back to that. But for now, this is Euler. Now, this is a sort of a simple method, and a somewhat more refined method is the following, and it goes like this. So first you calculate, you do more like an Euler step. You calculate what the derivatives are at Tn and Yn, and then you multiply with the step size, you add it up, and then you get like an Euler step, but I call it with a star because it's like a first approximation. Because this first approximation now I'm using to get a better approximation of the new point, and that is I'm taking not one derivative, but I'm taking two derivatives. I'm taking the derivative, the initial one at the beginning point, and I'm taking the derivative at the estimated endpoint, so Tn plus 1, and I have an estimation of this endpoint, and so I can estimate what the slope is there. And so I take like an average of these two, h over 2 times d, and that is my new thing. Okay, so this method has a name, and it's called Hoyne's method. And Hoyne is already in the 18-somethings. What is it, 1818s or so. It's in the book, there's a nice picture of him. And you can also read all about it, about his work. And that started, of course, when we first got these mechanical calculating machines. Then it was somewhat more easier to do calculations, so the schemes could be somewhat more complex. Now there is again a graphical interpretation for this. So let's draw it. So we have here this graph, we have time here. Let's say we have Tn, and here's the next step at Tn plus 1. Now the things we know, of course, are the past and this point. So we know Yn, and of course we know the slope, right? So we have this slope, which is called the function value at Tn and Yn. With that, we make this estimate. So on purpose I draw it like this. So y star n plus 1. So we have an estimate, and then what we do, we calculate what the slope is, and let's, for Pete's sake, assume that it's a bit different. It's this line. So this is the function value at Tn plus 1, comma y star n plus 1. So it's like an approximate thing. And then this slope and this slope, we take the average. Now that's hard to draw, but then times the time step, and then we will probably come out somewhere here, right? So this is then finally my Yn plus 1. So that is like a graphical interpretation of Hoyne's method. And of course this is h, right? This is step size h. So this is a nice way to visualize what is going on. And you also see that it's sort of a more like a curved thing, which I can describe. Now the big question is, of course, what is better? I mean, this is a lot of more work, and is it also better? And I wrote here refined. So we have to look into what do we mean by that? What do we mean by the word refined? And for that, we have to look at errors. And of course, how can we estimate the errors in the problem? So we have to look at errors. Look at errors we make in chopping off the Taylor series, because that is actually what we're doing. If you look at, for instance, this first step, this Euler step, then there are a lot of more terms coming up here. If we would write that down, like, oh, what would it be in the end? Well, yn plus 1 should have been yn plus h times, for shorthand I write now fn, because it's the function evaluated at that point, plus h plus h squared over 2 times f double, etc., etc. But if you look at this Euler step, if we do yn plus 1 equals yn plus h times fn, then apparently we make an error of the order, and that is h squared, right? So that is the truncation error we make. We call this truncation error. That's a truncation error. Now, it wouldn't be a surprise if you look at Hoyne, and if we write down eventually what Hoyne is, yn plus 1 is yn plus h over 2, and then times this f tn yn plus these f tn plus 1 yn plus 1, with the star, that the truncation error here is, of course, of the order h to the power 3. You can check that with a standard solution, standard differential equation thing, which we will look into later. But why is it better? Because the truncation error in this case is smaller. It's of a smaller order. And so we say the local truncation error, which we give the name, I use epsilon here, is as such. So for Euler's method, we see that the local truncation error is of the order h squared, and for Hoyne method, the local truncation error is of the order h to the power 3. So it's a bit more accurate one. But this is only for one step. But this is only one step. And what you want to do is, of course, you want to know what the global error is. So the global error is sort of the sum of all local errors. And how many local errors do you make? So how many of these local errors? Well, that's easy. If you say I'm going to integrate for a period, for the period of integration, time is t. Say you want to know the solution within an hour, then t is 1 hour, or you want to know the solution within 3 minutes, then t is 3 minutes. Then how many steps do you make? So the number of steps is then in the numerical integration is then, of course, n is this t divided by the step size, right? And of course, these number of steps is the sort of the sum of the errors you make. So we say that the global error you make, the global error is then the sum of all these local errors. And then for our case, this sum then comes down to t over h times these epsilons. And you see that the order then will drop down one. So for Euler method, and we have a capital E we use for that Euler method, we get then that the global error E is of the order h, and for Hoyne method it's the global error is of the order h squared. But that's still pretty good, because that means that if you have a solution and you want to have a more accurate solution, then what do? You just make a smaller step size, right? So that is actually the way to go. There's 1 minute left before the break. Then I see typo, yn must be yn plus 1. Yeah, which line? Let me see, yn plus 1. Oh, I quickly see no real typo here. But if you think that there's a typo, then just look in the book. There shouldn't be a typo in the book. Okay, for now we're going to do a break, coffee break or tea break. Yeah, and then I'll return in 15 minutes for the second part of the lecture. Above the drawing of Hoyne. This should be, this is correct. This is absolutely correct. Yeah, okay. Yeah, there we go. Stop the